Hi, this is K. Sai Chandra from CSEB section. The topic which I have selected for this TikTok is on the minimal general sum connectivity index of connected graphs without pendant vertices. Abstract. The general sum connectivity index of a graph G, denoted by x alpha P of G, is defined as a summation of UV belongs to E of G, where d of u plus d of v of alpha, where uv is the edge connectivity, the vertices u comma v belongs to v of g. D of w denotes the degree of a vertex, w belongs to v of g, and alpha is a non-zero real number. For alpha equal to minus 1 by 2 and n greater than or equal to 11, Wang et al. On the sum connectivity index, Flomat 25, 2011, 29 to 42 prove that K2 plus Kn minus 2 is the unique graph with minimum x alpha value among all the n vertex graphs having minimum degree at least 2, where K2 plus Kn minus 2 is the join of the two vertex complete graphs K2 and the endless graph Kn minus 2 on n minus 2 vertices. Thomas Q. Two connected graphs with minimum general sum connectivity index. Discrete application maths 178 2004 135 to 141 proved that the result of Wang et al. Holds also for n greater than or equal to 3 and minus 1 less than or equal to alpha less than minus 0.867. In this paper, it is shown that the aforementioned result of Wang et al. Remains valid if the graph under consideration are connected n greater than or equal to 6 and minus 1 less than or equal to alpha less than alpha naught, where alpha naught is similar to minus 0.68119 is the unique real root of the equation x alpha k2 plus k4 minus x alpha of c of 6 equal to 0 and c6 is the cycle of 6 vertices. Coming to the index terms, chemical graph theory, general sum connectivity index, topological index. So coming to the index terms, we have three different indexes. One is chemical graph theory, another one is general sum connectivity index, and last one is topological index. So these are the index terms. Introduction. Throughout this paper, the term graph refers to a non-trivial, simple, finite, and connected graph. Vertex set and edge set of a graph G will be denoted respectively by V of G and E of G. So throughout this paper, the term graph refers to a non-trivial, simple, finite, and connected graph. Vertex set and edge set of a graph G will be denoted respectively by V of G and E of G. The degree of a vertex U belongs to V of G and the edge connecting the two vertices U comma V belongs to V of G will be denoted by D of U and UV respectively. A graph with n vertices will be referred as an n vertex graph. Minimum degree of a graph G is the least number among all the vertices degree of G. A vertex V belongs to V of G of degree 1 is called pendant vertex. So the pendant vertex is the minimum degree of a graph G is the least number of among all the vertex degree of G. Those graph theoretic notation and terminology which are not defined here can be found in some standard books of graph theory like Article 12 and 25. Finding graphs from a certain graph family with external values of those graph invariants which found some applications in chemistry is the topic of many publications appeared in chemical graph theory. So finding graphs from a certain graph family with external values of those graph invariants which found some applications in chemistry is the topic of many publications appeared in the chemical graph theory. And the first Zabrak index appeared within the study of total pi electron energy of alternate hydrocarbons and radiac index proposed for measuring the extent of branching of certain chemical compounds are perhaps the most studied graph invariants regarding the aforementioned external graph theoretic problem. Details about the mathematical aspects of the first Zabrak index, respectively Randic index, can be found in the recent surveys, respectively, and related differences listed therein. Inspired by the work done on the Randic index and the first Zabrak index, Zo and Trijantic proposed the sum connectivity index, a variant of the both Randic index and first Zabrak index, and general sum connectivity index, the generalized version of both first Zabrak index and sum connectivity index. So, inspired by the work done on the Randic index and the first Zabrak index, Zo and Fijanti proposed the sum connectivity index, which is a variant of the both Randic index and first Zabrak index and general sum connectivity index, the generalized version of the both first Zabrak index and sum connectivity index. The general sum connectivity index of a graph G is defined as x alpha of G equal to summation of UV belongs to E of G, where D of U plus D of V power alpha, where alpha is a non-zero real number. The choice alpha equal to minus 1 by 2 corresponds to the sum connectivity index. It needs to be mentioned here that 2x minus 1 coincides with the well-studied harmonic index. The Randic index is actually the most widely applied graph invariant in chemistry and pharmacology. The chemical applicability of some connectivity index was tested and it was concluded that the predictive ability of the sum connectivity index and Randic index is partially same. Consequently, we may say that the sum connectivity index of as such important as the Randic index is. But why should one consider the general sum connectivity index in chemistry, particularly in quantitative structure property and structure activity relations? So we have a question that why should one consider the general sum connectivity index in chemistry, particularly in quantitative structure property and structure activity relations? Actually, the main advantage of using the general sum connectivity index is that the value of alpha can be determined during the regression procedure in such a way that the standard error of estimate for a particular studied property of molecules is as small as possible and the corresponding correlation coefficient is as large as possible. So the main advantage of using the general sum connectivity index is that the value of alpha can be determined during the regression procedure in such a way that the standard error of estimate for a particular studied property of a molecule is as small as possible and the corresponding correlation coefficient is as large as possible. Thus, it is meaningful to explore the mathematical aspects of the general sum connectivity index. In this paper, we prove that the graph which attains minimum sum connectivity index 44 found greater than or equal to 11, where minimum harmonic index 1545 found greater than or equal to 4 and minimum general sum connectivity index x alpha 42 for minus 1 less than or equal to alpha less than minus 0.867 n greater than or equal to 3. In the family of all n vertex graphs having minimum degree at least 2 also attains the minimum general sum connectivity index x alpha in the aforementioned graph class for minus 1 less than or equal to alpha less than minus 0.86119 and n greater than or equal to 6. Since all the graphs considered in this paper are non-trivial and connected unless otherwise stated, the class of graphs with minimum degree at least 2 is actually equal to the class of graphs without pendant vertices. So since all the graphs considered in this paper are non-trivial and connected unless otherwise stated, the class of the graphs with minimum degree at least 2 is actually equal to the class of graphs without pendant vertices. Statement of the main result and some preliminary lemmas. In order to state the main result, we need some definitions. By disjoint graphs, GAN H, we mean the graphs GAN hair vertex disjoint as well as edge disjoint. The joint of two disjoint graphs G1 and G2 is denoted by G1 plus G2 and defined as the graph with the vertex set V of G1 belongs union with V of G2 and the edge set E of G1 union with E of G2 union with U comma V where U belongs to V of G1 and V belongs to V of G2. Throughout this paper, joint will be taken over disjoint graphs. Complement of a graph G is defined is graph G with the vertex set V of G and the edge set U comma V where U belong is or 6 belongs to E of G where U6 equal to V. As usual, then vertex complete graph and end vertex cycle graph will be denoted as Kn and Cn respectively. Throughout this paper, we denote by alpha naught is similar to minus 0.68119, the unique real root of equation x alpha, where k2 plus k4 minus x alpha of c6 equal to 0. Now we can state our main result. Theorem 2a, if minus 1 less than or equal to alpha less than alpha naught and n greater than or equal to 6, then among all n vertices connected graphs having minimum degree at least 2, k2 plus kn minus 2 is the unique graph with minimum x alpha value, which is equal to 2 into n minus 2 into n plus 1 power alpha plus 2 power alpha into n minus 1 into alpha. For a non-empty set A belongs to V of G, denote by G to A the graph obtained from G by removing all the vertices of A as well as all the edges incident to these vertices. A non-trivial connected graph G is K connected if and only if G to X is a non-trivial connected graph for every X belongs to V of G with modulus of X less than K, bearing in mind the fact that the minimum degree at least 2, we have the next result as the direct consequence of theorem 2a. Corollary 2b. If minus 1 less than or equal to alpha less than alpha naught and n greater than or equal to 6, then among all n vertices, two connected graphs, k2 plus kn minus 2 is the unique graph with minimum x alpha value, which is equal to 2 into n minus 2 into n plus 1 power alpha plus 2 power alpha into n minus 1 power alpha. In the remaining part of this section, some lemmas are given, which play a vital role in providing theorem 2a. The first such lemma is related to the removal of an edge from a graph. Proof of theorem 1a. Proof of theorem 1a lemma 3a. Theorem 2a is true for n equal to 6. Proof. There are 61 non-isomorphic connected 6-vertex graphs with minimum degree at least 2. We generate these graphs by using SEG math. We calculate the general sum connectivity indices of these 61 graphs and then we compare these indices with x alpha into k2 plus k4, which gives the desired result. Lemma 3b. Let G be an n-vertex connected graph with minimum degree at least 2. Suppose that G contains at least one pair of adjacent vertices of degree 2. Also suppose that if U, V belongs to V of G is an arbitrary pair of adjacent vertices of degree 2, then either U, V have a common neighbor of degree more than 3 or u comma v have a common neighbor of degree 3 which is adjacent to a branching vertex, a vertex with degree greater than 2. If minus 1 less than or equal to alpha less than alpha naught and n equal to 7 or 8, then it holds that x alpha of g greater than 2 into n minus 2 into n plus 1 into alpha plus 2 alpha into n minus 1 alpha. If minus 1 less than or equal to alpha less than or equal to alpha naught and n minus 7 or 8, then it holds that proof. If the minimum degree of G is at least 3, then we may choose an edge V1, V2 belongs to E of G, satisfying the inequality D into D of V1 plus D of V2 less than or equal to D of U plus D of V for all UV belongs to E of G. Clearly, the graph G minus V1, V2 still have minimum degree at least 2, and by using lemma 2C, we have x alpha of g greater than x alpha of g minus v1 v2 for minus 1 less than or equal to alpha less than alpha naught. Thereby, it is enough to prove the lemma when g has minimum degree 2. So if the minimum degree of G is at least 3, then we may choose an edge V1, V2 belongs to E of G, satisfying the individual inequality D of V1 plus D of V2 less than or equal to U plus D of V for all U comma V belongs to E of G. Clearly, the graph G is V1, V2 still has minimum degree at least 2, and by using lemma to see we have x alpha of g greater than x alpha of g minus v1 v2 for minus 1 less than or equal to alpha less than alpha naught. Thereby it is enough to prove the lemma when g has minimum degree 2. Here is the photo for x alpha of h6 and all the values up to h6 to h22 and up to 39. So these are the values. Proof of the theorem 2a. We prove the result by induction on n. The result is true for n equal to 6, 7, 8 and minus 1 less than or equal to alpha less than alpha naught because of lemmas 3a, 3d and 3f. Now we suppose that n greater than or equal to 9, minus 1 less than or equal to alpha less than alpha naught, and the result is true for all those graphs of order at most n minus 1 whose minimum degree is at least 2. Let G be an index vertex graph with minimum degree at least 2. If the minimum degree of G is at least 3, then we may choose an edge V1, V2 belongs to E of G, satisfying D1 of V1 plus D of V2 less than or equal to D of U plus D of V for all UV belongs to E of G. Clearly, the graph G minus V1 V2 obtained from G by removing the edge V1 V2 still have minimum degree at least 2, and by using lemma 2C we have x alpha of G greater than x alpha of G minus V1 V2 for minus 1 less than or equal to alpha less than alpha naught. Thus we assume the minimum degree of G is 2. Here we have x alpha of G equal to x alpha of G5 plus 4 alpha plus 2.5 power alpha plus 3 plus D of U2 power alpha. So if we extend that, we have this completes the proof of the theorem 2a. Conclusion. We have proved that the graph k2 plus kn minus 2 which attains minimum sum connectivity index for n greater than or equal to 11, minimum harmonic index 15, 45 for n greater than or equal to 4 and minimum general sum connectivity index x alpha for minus 1 less than or equal to alpha less than minus 0.867 n greater than or equal to 3 in the family of all n vertex graphs having minimum degree at least 2 also attains the minimum general sum connectivity index x alpha in the aforementioned graph class for -1 less than or equal to alpha less than -0.68119 and n greater than or equal to 6. See theorem 2a. For sufficiently large n, we expect that the same graph k2 plus kn minus 2 has minimum general sum connectivity index x alpha in the above mentioned graph class also for -0.68119 less than or equal to alpha less than 0. It would be interesting in future to prove this assertion. So for sufficiently large n, we expect that the same graph k2 plus kn minus 2 have minimum general sum connectivity index x alpha in the above mentioned graph class. Also for -0.68119 less than or equal to alpha less than 0, it would be interesting in future to prove this assertion. But we remark the technique mathematical induction adopted in the present paper would not work well in this regard because the verification of the induction based step would be much more tedious as n would be increased when we considerably increase alpha in the interval of -0.68119, 0. I thank the faculty and the college for providing me this opportunity to speak on the topic. Thank you.